A couple quick caveats. I expect audience participation. I know you're eating, but shout things out when I ask for some help. Otherwise, this is going to be really long and not as fun. I want to talk about making AI accessible. I think this is really important because AI can solve really difficult problems and make the world a better place. You notice there was a subtitle with Python, right? Python's got the most mature libraries in the space. It's where all the domain experts are. It's where all the interesting work's being done. Sorry if you prefer a different language for this, but I think that's where we are. And this is really the most important subtitle for the non-developer, or to the non-developer. Domain experts are trying to solve some really hard problems, and they're running into some issues with tooling that isn't designed for consumption by them. I'll talk more about that in a little bit, but I want to drive home on that because I'm hoping that a lot of people in the audience, and this is a lot of what I got when I was talking to people out there earlier, are either domain experts trying to solve these problems, pick up some of these tools and learn about it. You're new to the AI space. Non-experts already in these tooling is what I'm saying. I think that's the key here. Quick note about us. My name is Robert Herbig. I've got a decade plus of software product development experience at SEP. My colleague in the back there, wave your hand. All right. Jordan Thayer, you may notice his name tag says Seabass. Make sure you ask him about the story. Go fishing for the story if you... Fishing for the story. Okay, all right, okay. All right. He's got a decade plus of experience in AI research. He's recently come to SEP to work with me on this project. We are professionally vested in making these techniques more accessible and using them to help our clients solve their hard problems. We work at SEP. We're a custom software consultancy, and we solve hard problems for our clients who are typically non-software development shops. Tying that into the whole theme of this right now is what we've been doing for the last while is trying to work with domain experts who are experts in some technology that's not software, not AI, not machine learning, and help them solve the problem. So I want to share with you some observations, some things that we've seen in working with a variety of different clients and domains, the common pitfalls that these non-AI experts fall into, and then some of the ways that we've helped them be more successful and more efficient in their work. All right. Here's what we see. Companies have data. Raise your hand if you were surprised by that statement. Perfect. All right. Companies have data. Lots and lots of data. I'm going to take a step back and give a little bit of historical context here. 2005, circa 2005. I want to be clear. I'm going to put some dates up here, and they're plus or minus a couple years. Bear with me. Circa 2005, companies have been gathering data kind of passively. It wasn't a huge focus. They knew they could do something with it, and something real interesting started to happen around the turn of 2005. Any thoughts, any ideas on what may have made a significant impact around then? There's a reward. We've got prizes. Any thoughts on what could have happened around this time frame? Any suggestions? Housing crisis, I heard. I love it. Not what I was going for. I was going for exposure of data breaches. You can see from this graph, just within 3 years, 2005 to 2008, 4 times more data breaches and exposure per year. And that has gone sharply up. Don't pay attention to the downtick at the end. 2018 wasn't finished when this graph was generated, so it's just gotten worse, I promise, especially over the rest of this year. Yeah, make sure you give them a prize. Thank you. The point is, companies had to ask themselves a very interesting question. Is data an asset or a liability? What would make it an asset? Any guesses? The information you can pull from it? What could you do with that information? You could figure out who your client base is, where they're spending money, why they're spending money, and use that to drive your revenue. Right. You could turn that asset into income with learning things from it. Perfect. What could make it a liability? What? The fact that you have it, right, and that, right? So that's where we're at. Companies were asking themselves that very interesting question. They hadn't really thought about it in terms of liability. There were little exposures here and there, but this is sort of the situation you ran into. In 2005, Netflix was running its competition, $1 million prize for anyone who could improve its recommendation system. Sorry, I'm getting some feedback. Am I in the right place? Good. Okay. So $1 million prize, right? That's pretty cool. And they were clearly interested in that to put some real money behind it, right? So they saw some opportunities to turn that into revenue. At the same time, Card Systems Incorporated had the biggest breach, largest hack to date. They are a credit card processing firm, and because of that hack and that breach, they lost Visa and American Express, which is kind of crippling to a credit card processing company, right? So this really started coming to a head, and you saw that graph where things quickly spiked up. They were confronted with this, right? Before they were just kind of hanging on to it. It might be useful, but they hadn't confronted the reality. Circa 2010, okay, there's clearly ways to turn it into revenue, to turn the asset into income somehow. Clearly, it can be a liability. We need to put into place better practices, right? So companies pretty clearly decided this is the right path forward, and this is the question they asked themselves. How do we turn this asset into income? You gave a few examples. I think that's a pretty good way. Do something with it, learn something with it, and turn that into increased revenue, right? Primary example, Google AdSense. 2010 was about the year when Google AdSense started using search history to improve contextual matching and offer more relevant ads. They were using AI to turn that data into better revenue. But then something happened. In 2015, any guesses, 2015, what happened? People started asking, how do we do that better? What's your favorite answer? What's your favorite tool? Any suggestions on how we can turn that data into income better? Gentleman with the blue hair. Okay, all right. GPUs got more expensive to buy because of Bitcoin farmers and right. Okay. I love where you're going with that. I want to point out TensorFlow released in 2015 and SageMaker released in 2017. So this is when we started to see more powerful tools solving more difficult problems being released for, let's call it prices that people could actually pay without hiring a dozen PhDs and staffing up an entire department. My argument is, today, and it's circa 2020, right, today, the question now companies are facing is, how do we get there faster? That's what I'm trying to tie together here, is what we are seeing is companies want to get there faster. And the way they do that is they leverage their domain experts. Companies have domain experts. These are electrical engineers, mechanical engineers, accountants, medical professionals. They're not programming experts. They're not anything but in that domain, right? They know they have the data. They know we've seen examples of how we can use it to improve things. How do we get there? Machine learning is a great example of that. You have a lot of data. You can do something with it. You know you have answers in that data somewhere. You can mine it for those things. So now we're seeing where a lot of domain experts want to use machine learning, which is, by the way, for context, a subset of AI that I'm going to focus on here for a minute. But the problem is, like I said, they're not experts at programming, and they're not experts at machine learning. They can occasionally solve a problem. Domain experts are learning these tools. There's a lot to learn. And the trick, though, is to get there and do these things repeatedly, reliably, and efficiently. That's what we're trying to do. Because right now, becoming a machine learning expert simply takes too long for those domain experts to basically pick up a second background, a second education. The way I like to phrase this is that these domain experts are implementers by necessity and not by choice. And if we can improve that tooling and improve that experience, we can make them more efficient. Someone was asking how you get started. Here's the answer, right? This is just a handful of frameworks, right? There are more than this. There are several that are still active, even if they're not being actively maintained. They're still actively used a lot. This is a lot. If you add up all the API documentation for all of these frameworks, there's a degree, right? There's a college degree in there trying to learn all these things. The APIs are inconsistent. They are large. They're super powerful, right? Let's acknowledge this. There's a lot of benefits to having these two. These can solve a lot of different problems and do it very well. But there's a lot to learn, just at the API level for these frameworks. You have to learn some of the underlying theory, too, which is 10 times as big as the APIs that we saw. And often you need to learn that underlying theory in order to choose which tool to use for the job, because they solve different problems and they're a little inconsistent in that way. If you had a domain expert who was interested in this 10 years ago, when it was really nascent, that'd be great, and by now they'd be really good at solving this problem. Unfortunately, a lot of domain experts are only realizing this in the last few years. they haven't caught up with all of that learning, and this situation doesn't help them out today. So I'm going to talk about some of the common pitfalls that we've seen over and over, and I hope that those of you who are domain experts looking to use these tools can sort of see these things and keep an eye out for them next time. If you're maybe a developer working with those domain experts, then I think that these are good things you can help work through and help them avoid. Frameworks don't focus on data preparation. So there was a study done last year by, I believe it was by Gartner, and it said that a large percent of the time that data scientists spend solving problems is actually spent on data preparation. Does anybody know what percent? Sorry? Heard the number? 80? You got it in one, I'm impressed. 80% of data scientists' time, the machine learning experts' time, the people doing this full-time, solving real hard problems, 80% of their, did you know that? Did you read the article? Oh, okay, all right. That's okay, you still get a prize. You got me the answer I wanted, so it's good. 80% of their time is spent, I'm sorry, did someone else say it too and I didn't hear it? Okay, well, good job, Josh, I'm impressed. Josh and Adam both get a prize. 80% of the data scientist time, again, full-time, doing this for real, solving hard problems, 80% of their time is spent just cleaning up the data, preparing it, so that they can then do something interesting with it, learn from it. So any gain we can do here is going to have a big impact on the overall time to solve these problems. Tied into that is visualizations. These domain experts, it's actually kind of fascinating. We've worked with a couple who we could throw a few numbers on the screen, and they'd go, oh, well, that's clearly characteristic of a fuel leak. Okay, great. They can recognize those things. But when you've got millions or billions of rows, it's too much for a human mind to comprehend. At least, no, I can't, and no one I've met can. A picture's worth 1,000 words, and what the visualizations can do is give a very powerful way to make some insight into the shape of the data, as well as what you can learn from it and what you can do with it. Maybe it has to change, you might have the wrong data to answer your question, that kind of thing. So a quick visualization can answer that question much earlier in the process than a lot of this framework suggests, and it'll save you a lot of time trying to get to a point at which it doesn't work. Failure messages. Many libraries are inscrutable. Okay, quick show of hands, more participation. Raise your hand if you've ever seen an error message on a program you're trying to write and couldn't figure out what it meant or didn't help you debug the problem. Okay. I'll raise both hands, okay, because like that happens all the time, and I've been doing this for over a decade, right? That is the state of the art, unfortunately. Failure messages, they're not too helpful. I'll give some examples later, but for those of you who didn't raise your hands, count your blessings, because it's only a matter of time. All right, and lastly, some easy-to-make mistakes are catastrophic. So unfortunately, what these frameworks make very easy is either making mistakes in the first place, or making it very hard to detect that you've made a mistake, or making it hard to recover from and find the root cause and then fix it. Like I said, I'll give a few examples. So these are some guardrails that we've found useful to put in place to help the domain experts get to a useful place a lot faster. Making necessary steps easier and safer. There are a bunch of things that you simply have to do to solve a problem with AI or with machine learning. What's the first step? Anyone?
Acquire the data.
Acquire the data. Okay, perfect. What's the second step? Clean it. All right. So someone's paying attention. Good. What's the next step? There's no right answer here because it highly depends on what you find. So explore. Right, exploration. Exactly. Give that man a notebook. Everyone. Okay. That is perfect. Those are things you have to do all the time. I love reading examples of using AI or ML online because here's this database, do this, apply this technique, do this. Hey, look, it recognized things. And that's cool, but it's never that easy. This is a very much, and I think those articles give a false sense of security that when you get to your problem in the real world, you can do that. That's not the case. This is a very experimental approach. You've got to come at this with a mindset that it is an experiment. You'll have to go through several iterations. Take your data, right? Acquire your data, clean it, explore a little bit, clean it a little more. Once it's in a good place, try some learners, try again, analyze the results, iterate on those, and tune them, and so on. So That's really where we're at, and that's what needs to be made easier and safer. The next one is providing tools for visual inspection. I touched on a little bit with the pitfalls, and I'll give some examples right now. But that cycle of cleaning data, exploring it, repeating back and forth is really common. So here's a visualization of some data. This is a probability density function. So this is a graph of continuous data. What can you observe from this graph? What do you take away from looking at this graph? Someone, you got to speak up. It's a little hard to hear up here. Something went down? Right, so something started. Okay, so probability density function. So this is the probability that any given point in the data set is at one of those values at the bottom. So you can see that the vast majority of the points is very likely that any given point is a 0, and then far less likely that any of the points are after that. So, thank you. Any other observations? Anything interesting that you'd want to look into from this data? It's too perfect. Yeah, that's right. That is a very good insight. This is suspicious to me because of that. I agree with you. And if you notice, it might be hard to see on the projector, but right around between 0 and 2, there's a couple little peaks there that are real hard to see. The data is too linear because it is swamped by all of the zeros in the data, basically. So we may have to apply a transform. Any suggestions for a good transform to get a little more insight into what's going on here? Log 10, hey, thank you, gentleman with the blue hair, who named Jordan, who I've never met before. Give yourself a prize. So log 10 is a great transform to splay the data and get a little more insight into what's going on. Yes, Josh? A way to manipulate the data, that's all it is. So you would apply log 10, a log operation, logarithmic operation, to every data point. And you could see the data as something a little more like this. Sorry, to the graphing, not to the data points themselves, to the graphing of the data, sorry. So now we can see that 0 is clearly the most likely item, right? But now we've got something much more interesting at all these data points after 0. So you can see the peaks. What's the first peak approximately at? 1. What's the next peak approximately at? Value 2? Okay, right. So you can see that there's a peak at about every integer and a valley for everything else. So that's a good hint to me that this isn't actually continuous data and we're graphing it wrong. We just started at the wrong place. That's the kind of thing that we can learn real quick instead of wasting our time trying to apply learners that are treating it in the wrong way and are never going to get us anywhere near the right answers. Another visualization is correlation. So this is a heat map of correlation. So what we can do is take an image, an 8x8 image, 8x8 pixels, sorry, which results in 64 dimensions, right, 8 times 8, and we can see which of those dimensions are correlated to the others. Correlation is simply how related are they to each other. So yellow in this case means that they are highly correlated. In fact, they are nearly identical to the point where machine learning is not going to be able to learn anything new if you have both columns versus one. It's just noise. There's nothing added to the predictive power by having that second column in there. See if I can get this to work. Hey, all right. So here you can see that right across the top, there's that solid yellow. Same thing on the border here. And then those are indicative of, in this case, there's a border around the image. Not useful if every single image has exactly the same border, right? But by seeing it on this heat map, it was a real quick way to inspect the data and say, there's something suspicious there. We probably need to do an additional step of cleaning it up. Other interesting things here, so I'll point out real quick that this diagonal is in fact exactly expected because it's the identity. It's each column compared to itself, which should be perfectly correlated. If it's not, something has clearly gone off the rails here, and math doesn't work. So we've got much more fundamental problems than how to learn data from how to learn something from this. All right. Another common step that has to happen, someone called it out. I believe it was Scott? John? Did I forget your name? You commented that exploration. And that's exactly right. very often, unlike the examples that you'll find on the internet, we don't know exactly which learner is going to be best. We don't know exactly what parameters to give it, and we need to tune those things. So here's an example of putting some guardrails around comparing different learners. You can see that there's a whole list of learners. We don't know which one's going to be effective on this data, so we'll run them all. It's just processing time, right? Let the computer spend its time doing that, and we'll do more interesting things. This is pretty close to the approach when you're first looking at a data set. You might even do this before you've done much cleaning, and just kind of get a baseline. Okay, this learner is probably not going to do very well. This one started off all right. We can focus our attention there, try and make it better. Especially interesting is to visualize the results of those learners. So you can look at a bunch of numbers. What was its precision, its accuracy, its recall, all those numbers, but it's hard to compare those things, and there's a lot of nuance to those. This is a visualization that's real interesting. If you see this, red are the data points, and the green are the data points that we're trying to predict. So from this, I can pretty quickly tell it's not going to work. There's no way the computer could draw something or could in any way classify those things differently than each other. There's no way to really make red and green distinct from the learner's perspective. They're right on top of each other, they're superimposed. There's no way to classify them. So we've saved ourselves a lot of time, though. We didn't spend a lot of time trying to clean the data and go through all these steps over and over and over. We know right here, this learner is not going to work with this data set. One of those two things has to change. On the other hand, if we see a graph like this, we know we're on the right track. So the computer here has said red, green, and black are 3 different classes, right? You can pretty clearly see how these are divided up, and you can understand how the machine could say, yeah, these are grouped in this certain way. So from there, I'm feeling real confident. And it turns out that this was this the IRIS data set? Yep, IRIS data set. It's a freely available data set. It's great for getting your feet wet with machine learning and with AI. So in fact, this concept is very learnable, and we were able to do that. So it's pretty reasonable, and it's a good starting point. This is another example. This is back to images. This is looking at the classification of digits. So what we've done is we've color-coded the 10 digits from the MNIST digit database, another freely available set that a lot of examples will use. So this is 8 by 8 pixels, so 64-dimension data, embedded in a two-dimensional space. And you can see that we've got pretty good clusters. Try the spotlight thing again, and here you go. So you can see that while it's not perfect between green and yellow and cyan, it's pretty close. And you can see how with a little more tuning, we could probably get there. Same thing with there's some overlap here, and for each of these colors, there's even a little noise with black, right? But it's not bad. It's a good starting point. So we've quickly learned, yeah, this is probably a reasonable approach. A lot of this noise up here, for example, is probably things like 3s and 8s that are pretty similar, which makes sense when you think about digits and numbers. All right, fail early, fail loudly, fail verbosely. Back to those cryptic error messages that we see. So here's an example. This was some code written in TensorFlow. Can you read this in the back? No, you can't? It's unfortunate. Well, even if you could, it wouldn't tell you much, and that's kind of the point I'm trying to make, right? So the quick synopsis is, there was an error, there's a stack trace, value error, but during the handling of this exception, another exception occurred, and it is a type error. I'll give you a hint. None of the line numbers here are where the problem actually is. Most of the line numbers are, in fact, deep down in libraries. And I want to know, can anyone spot the error? I'll make it real quick since it's hard to read for some people in the back, but I'm curious if anyone can tell what the error is. Okay. Good guess, not the problem. Josh? You got it. All right, perfect. So as Josh was pointing out, right up here, we have a 0 that should actually be a 0.0. But that's a pretty subtle problem and real easy to mistake. And the debugging stack trace tells you there's a type error, which is correct, but doesn't really tell you where and help you get closer to the problem. So these are the kind of cryptic error messages that at least I've banged my head against for years. I want to call back for a second. How much time of a data scientist's time is spent cleaning data? 80%, all right. So I posit that if 80% of their time is spent cleaning data, the other 80% is spent debugging these kinds of things made difficult by the framework. Here's a different example. This is one of the engagements that we had with some domain experts who wanted to solve some problems. We put some guardrails around it. And there is very clearly another problem here in this code. Can anyone tell me what that problem is? Expected number of neighbors to be at least 1, value error. Yeah, who said that? Sorry. I heard a 0 somewhere. Yes, so the number of neighbors, k means up here, is 0. Our line of code down here, somewhere over here, I'm sorry, I can't see it from this side. Our line of code down there has the line number, which corresponds to k-means taking a 0, and that's an invalid value, right? So it's real quick feedback, and you can address your problem. It's not exactly a Python convention, but it is pretty common to try and execute for as long as possible and fail at the last possible moment. Unfortunately, that doesn't make things beginner-friendly. So yeah, I'm not going to say it's against the convention, but it's not typically seen. But this does help people who are new to the environment, new to the framework and the tooling, is failing early. All right, alongside failing is the ability to be a little more verbose with what's going on. Domain experts don't have always a great model in their head of what the machine is doing, unlike expert programmers. So a lot of the frameworks aren't very verbose. So one of the things that we can do to help out domain experts is making them more verbose. Use more print statements, use more logging, be a little more explanatory with what's going on in the machine's brain, so to speak. All right. Last example of guardrails, I think, is guarding against easy to make mistakes. So we've seen some of those before, but I'll give you one more example, is using this data set as our example. What we have first are 2 ID columns. And one of the things, so anyone familiar with databases, raise your hand. All right, so this is basically a composite key in a database. They are the columns that together uniquely identify each row. That's necessary so that you can sort of understand which rows had which impact on the learners. And anyway, an easy mistake to make with a lot of the existing tooling and framework is to accidentally use those identification columns in your learning. Well, they don't have any predictive power. Generally, they don't have any predictive power. They uniquely identify a row, but that doesn't help the learner make some decision with them, again, generally. A lot of the frameworks, you just supply an index. Is that index 0-based, 1-based? Is it inclusive? Is it exclusive? It's real easy to make a mistake there. Who's ever made an array indexing mistake? Yeah? Okay. All right. Anybody written code? The student even has encountered that before. So see, this is really common. And those frameworks make it real easy to make. If you can find a way to have a harder separation between those things, so perhaps they're stored in 2 different structs, or you have one data structure that keeps them separate in some way, you can avoid this class of problems. This is only one example of easy to make mistakes. Another one is here. Curious, does anyone immediately spot the problem here? This one's a little bit of a long shot, but I'm hopeful. I'll give you a hint. When you have a learner and you want it to be able to predict something, you need to give it some training data. You usually take your data set and you split it into a training set, which the learner learns on, and then you split it, the other part being a test set that then you use to evaluate its behavior. Here we're attempting to evaluate the behavior of a series of learners. All right, it's worth a shot. The problem is on line 41, where we're handing it the training data to evaluate on. This is a bad habit because you can overfit and some other bad things can happen. That's why you want to reserve the data into 2 buckets. But if you can make errors more detectable and readable, that's also a benefit. They don't have to be, strictly speaking, throwing errors or logging or that kind of thing. Even readability helps avoiding whole classes of problems that will cause a lot of wasted time. All right, I got the 10-minute flag. I'm still above 5 minutes? Good, good. So I want to go ahead and start to wrap up then. Here's what we've seen. I can summarize it all with the current framework is not designed for domain experts to pick up things, pick up these tools and use them, but that is the best way that we can scale the learning and the capabilities and the usage of AI. What do we do about that? This is a lot of great tools, but they don't help solve that problem of getting domain experts up to speed. The end user is not a machine learning expert, an AI expert, or a programming expert. One such solution that we have built for one of our clients is an API that wraps some of these common frameworks and gives them a common interface. It restricts their choice, which might sound counterintuitive. Raise your hand if you thought that sounded like a good thing. Okay, that's what I expected. Yeah, Jordan did, of course, but hold on to that thought. And I want to point out that restricting choice in this case is actually a positive thing, because it keeps them, the novice AI machine learning domain expert, focused on the tools and techniques that are more likely to be relevant to them at first, more likely to be useful to them and powerful at the beginning of their journey. It prevents decision paralysis, and it lowers the barrier to entry. That's really what we're looking for. The other thing that this API did was it caught common mistakes. I showed you that example of k-nearest neighbors has to be greater than 0, otherwise it's not a very useful algorithm. And it avoids things like those data type errors that whole classes of errors that don't need to happen. It's not the only solution, but it's one way to move forward and make this scale a little better. Thank you. Any questions? Yes, sir.
Yeah, let me give you the microphone so we can get this on the recording.
So you've wrapped an API around a whole bunch of open source toolkits. Is the API itself open sourced?
Unfortunately, it is not. As a software consultancy, we built custom software for our clients that was proprietary for them. But it is something that could be done. Yeah. It's a great question.
Any other questions for Robert? No one else? All right. Well, thank you again, Robert, for joining us today and giving us some intros to AI and making it more approachable. I want to thank you for being here. Let's give another big round of applause.